Dear students, welcome to our next lesson on model-driven software engineering. The topic of today's lecture is model-driven architecture, and namely, we will be talking about meta-modeling and meta-leveling. Today, we will cover meta-modeling and levels of abstraction. And namely, we will be talking about 4 different levels of abstraction. The basic underlying motivation for the MDA is to improve productivity in software development process. That is to increase the level derived from a given amount of effort. It delivers this benefit first by raising the level of abstraction at which primary software artifacts are written. Second, by reducing the rate at which these artifacts become obsolete. The first goal aims to improve the short-term productivity of developers in the same way that high-level programming languages increased productivity in the 60s and 70s by obviating the need for programmers to write assembler or binary code directly. Modeling languages can further increase productivity by making it unnecessary for developers to write programs at all, become the primary artifacts developed by humans, and code will be a derived artifact generated by tools, for example, model compilers. This will allow developers to focus on describing business logic and problem concepts in as concise and abstract manner as possible, leaving tools to handle the routine implementation issues. Increasing short-term productivity is only one part of the overall picture. However, it is also important to improve long-term productivity by minimizing the sensitivity of primary software artifacts to change. We therefore believe that the second and in fact more important goal of the MDA should be to maximize the useful lifetime of key software development assets. To this end, in the following we identify the end user benefits which we believe the MDA should be designed to deliver, and then distill these into a concrete set of requirements for an MDA infrastructure. After criticizing the current approaches for providing such an infrastructure, we discuss what enhancements are needed for the full promise of the MDA to be realized. To increase the useful lifetime of primary software artifacts, it is necessary to reduce their sensitivity to the inevitable changes that affect the software system. It is impossible to avoid change at all, but by managing changes appropriately, their impact on software development investments can be minimized. 4 main kinds of change in particular need to be carefully managed: changes related to deployment platforms, changes related to development platforms, changes related to requirements and personnel. In today's rapidly changing deployment platform market, it seems that as soon as developers have mastered one new platform technology, another comes along to take its place. By documenting core business logic in platform-independent artifacts, however, it can be decoupled from the high rate of change in platform technology. The key to making this work is to automate, to the greatest extent possible, the process of obtaining platform-specific software artifacts from platform-independent ones through the application of user-definable mappings. If software artifacts are dependent on the platform development environment and tools that created them, their lifetime will be limited by the lifetime of the development platforms. This implies that artifacts should be decoupled from development environments by requiring tools to support high levels of interoperability. Effectively managing requirements changes has always been a big challenge in software engineering, but has recently been complicated by expecting deployed enterprise applications to be continuously available, even in the presence of significant changes to the business logic. It follows at a technical level that in addition to supporting the static addition of new types at development time, Deployed systems are expected to support the dynamic addition of new types at runtime. As long as certain vital development knowledge is only present in the minds of developers, such information will be lost in the all too frequent event of personnel fluctuations. It is therefore not only essential to embody all such key knowledge within the primary software artifacts, but to also describe them as concisely and appropriately as possible, maximizing the ease with which they can be understood by all interested stakeholders. This requires that primary software artifacts can be expressed using a concise and tailorable presentation. Clearly, all these different forms of change can occur concurrently, so the techniques used to accommodate them must be compatible with one another. Historically, one of the most effective ways of limiting the sensitivity of software to requirements changes is to structure them according to the principles of object orientation. Concepts such as encapsulation, polymorphism, and inheritance allow one part of a program to be extended without other parts being affected. However, in its traditional form, object-oriented programming is not well suited to handle the dynamic addition of new types. To meet this requirement, meta-concepts are needed as well. Meta-level description techniques in general are also useful for supporting the above-mentioned user-defined mappings and interoperability requirements. All these requirements are best dealt with by establishing a definition of meta layer above the subject of description so that humans and tools can systematically access and manipulate it. Finally, as evidenced by the success of the UML, the technology that has the best record of supporting concise presentation of information is graphical modeling. Again, however, it must be enhanced with meta-level description techniques to fully support user tailorability. Thus, the best strategy for realizing the main goals of the MDA vision is to leverage the synergy between object orientation, meta-levels, and modeling. In short, to utilize object-oriented metamodeling. Based on the above discussion, we can identify the following concrete list of requirements that an MDA infrastructure should ideally support. It should define, first, the concepts that are available for the creation of models and the rules governing their use. Second, the notation to be used in the depiction of models. Third, it should also define how the elements of a model relate to or represent real-world elements, including software artifacts. It should also define concepts to facilitate dynamic user extensions to item number 1 and item number 2, and models created from them. It should also define concepts to facilitate the interchange of item number 1 and item number 2, and models created from them between tools. It should also define concepts to facilitate user-defined mappings from models to other artifacts, including code. Having established a list of such abstract requirements, we are now able to evaluate various approaches with respect to the extent that they address these requirements and the elegance they display in doing so. Since the MDA is a relatively new vision, the OMG community is still in the process of adapting its standards to fully support it. At the heart of this adaptation process is the impending update of the UML and MOF modeling and metadata standards. While most members of the OMG community would agree that object orientation, meta levels, and graphical modeling all have a role to play in supporting the MDA, they do not all agree on the relative importance of their respective roles and how they should be integrated. Historically, the UML and MOF standards have focused on requirements from 1 through 3, identified above in this slide, by viewing the UML metamodel and the MOF as essentially having the role of defining languages. The UML metamodel is viewed as defining the language for creating models, and the MOF as defining the language for creating metamodels. While this is understandable given that the first 3 requirements essentially ask for an abstract syntax, a concrete syntax, and the semantic definitions, that is, a traditional language definition, this approach does not scale up to satisfy all the needs of an MDA infrastructure, as characterized by requirements 1 through 6. In particular, limiting the role of meta-levels to simply defining languages has the following concrete shortcomings. First, users need to be able to extend both the abstract syntax and concrete syntax dynamically. The provision of this feature is best dealt with by providing a meta-level above the user modeling level, which is not a classical language definition level, but a domain meta-level containing user metatypes. This level defines the library of modeling elements available to modelers. These concepts all share the property that their instances can be instantiated, that is, they are metatypes, and that they are typically specific to a certain modeling domain. Second, the traditional language definition approach does not naturally accommodate the type-instance duality of elements, which manifests itself as soon as more than two levels are present. When something has been instantiated and can itself be instantiated, it has both an instance facet and a type facet. The traditional approach must then explain how certain features of an element belonging to the type facet have an effect on some features belonging to the instance facet of elements derived from it. Third, the language definition metaphor on its own does not address the need to define mappings. The systematic definition of mappings from user models to other representations requires a meta-meta level defining the language used for defining modeling languages. Yet for mappings to be available for both the modeling and instance level, such a level would need to play two roles at the same time. It would need to be the definition level for M2 concepts and somehow provide interfaces to elements at both levels M1 and M0. This is the dilemma that the MOF is currently facing. On the one hand, it is trying to act as the UML meta-meta model, and on the other hand, it is supposed to standardize modeling repositories, potentially containing elements from all levels, including M1 and M0. These two roles cannot be reconciled with each other if one assumes the usual premise that each level exclusively defines just the level below it. Fourth, traditional language definition does not address the need for interoperability. Again, an additional meta-meta level is required. While multiple meta levels are certainly not incompatible with the traditional language definition approach, the resulting combination is not very economical in terms of concepts and techniques required and the individual level contents needed. In this presentation, we have discussed the metamodeling aspects of software engineering, which represents yet another level that is above of models. We have also discussed why MOF can be useful and what problems it resolves. Understanding the modeling, metamodeling, and meta-metamodeling concepts are critical in this course, as you will have to build the metamodels for your graphical languages that are key to implementing MDA transformations. Thank you very much.